So let's start. So in the previous class, we have discussed the fundamentals. How does this Raman how does Raman scattering takes place? How it is different from Rayleigh scattering? ये सब चीजें आपने सीखा है. And we have also learned different quantum mechanical viewpoint and the classical viewpoint to explain the events that happen. Stokes, anti-Stokes scattering. Then we had also discussed the conditions which make a molecule. Okay, so this is something that we have to continue. We were discussing this point. When a molecule becomes Raman active, what are the conditions that it must fulfill to be Raman active? Okay, so ये जैसा कि हमने बताया था, so basic thing, the fundamental thing that we expect that is important here is polarizability. In case of infrared absorption, microwave absorption spectroscopy, in those two cases you had the change in dipole moment during the particular event, rotation, vibration. During that particular event there must be a change in uh, dipole moment during the motion, that kind of vibration or rotation. तभी वो इंटरेक्ट कर पाएगा इलेक्ट्रिक फील्ड वेक्टर से. ऑसिलेटिंग इलेक्ट्रिक फील्ड, ऑसिलेटिंग डाइपोल इंटरेक्ट्स विद ऑसिलेटिंग इलेक्ट्रिक फील्ड. दैट वाज द क्राइटेरियन देयर इन इंफ्रारेड स्पेक्ट्रोस्कोपी. यहाँ पे क्या है, देयर मस्ट बी अ चेंज इन पोलराइजेबिलिटी. देयर मस्ट चेंज इन द पोलराइजेबिलिटी. सो बेसिकली जब कोई मॉलिक्यूल एक्सपैंड कर रहा है या कॉन्ट्रैक्ट कर रहा है तो उसका मॉलिक्यूलर वॉल्यूम चेंज हो रहा है. मॉलिक्यूलर वॉल्यूम का मतलब इलेक्ट्रॉन, most of the volume is the electron cloud. So electron cloud फैला हुआ है, it is more spread out if it is stressed condition, if the molecule is in stressed condition, and it will be easily distorted if an electric field is applied. अब ये इलेक्ट्रिक फील्ड अप्लाई जो होगा कहाँ से आ रहा है, ये लाइट में है. जो इलेक्ट्रोमैग्नेटिक वेव्स है उसी में तो इलेक्ट्रिक फील्ड है. सो दैट इज हाउ. So there is a change in polarizability. So imagine a hydrogen molecule which is undergoing vibration, stretching vibrations. So you have at each point of, as it vibrates, as it stretches and compresses, there is change in the molecular volume. There is change in the space, that overall space that electron cloud is occupying. So जब स्ट्रेच कंडीशन में होगा, इलेक्ट्रॉन्स विल बी मोर स्प्रेड आउट away from the nuclei, they will less tightly held, और distortion ज़्यादा produce होगा. So we say that polarizability is more in hydrogen molecule when it is uh, in stretched condition. In contrast जब वो compressed होगा, contracted condition में होगा, तो उसमें polarizability कम होगी. polarizability कम हो जाएगी क्योंकि जो इलेक्ट्रॉन्स है, इलेक्ट्रॉन क्लाउड is contracted, that is now occupying small space. It is now tightly held by the nuclei. So ये एक आपका imagination है. So okay, so this is how you start visualizing the things and then becomes. अब यहाँ पे भी ये भी चीज़ आती है कि इसको कैसे रिप्रेजेंट किया जाए. हाउ टू रिप्रेजेंट द पोलराइजेबिलिटी on paper, on cases. So it is done by drawing an ellipsoid. एलिप्सॉइड मैंने आपको कहा था कि एक एलिप्स को आप 3 डायमेंशनल स्पेस में एक बार मेजर एक्सिस के अलॉन्ग रोटेट कर दीजिए, एक बार माइनर एक्सिस को के अलॉन्ग रोटेट कर दीजिए, तो जो 3 डायमेंशनल शेप बनता है उसको एलिप्सॉइड कहा जाता है. ठीक है. सो दिस इज अ पोलराइजेबिलिटी एलिप्सॉइड दैट इज ड्रॉन. और एलिप्सॉइड ड्रॉ करने की जरूरत क्यों पड़ी? बिकॉज पोलराइजेबिलिटी इज अ टेंसर. ये मैंने आपको बताया था लास्ट क्लास में. दिस इज अ टेंसर क्वांटिटी. इट इज नॉट अ वेक्टर, इट इज नॉट अ स्केलर, इट इज अ टेंसर. और टेंसर में आपको 3 चीजें होंगी. यू हैव मैग्नीट्यूड, direction and reshape. So three dimensional एक shape भी geometrical एक shape भी होगा. Okay, so okay. Okay, I hope now it is showing the slides. Hello. Okay, so polarizability, ellipsoid. So we draw ellipsoid to show, as polarizability is a tensor, we have to show the three aspects: the magnitude, the direction, and the geometrical shape, three-dimensional shape that it has. So essential condition for Raman activity is that molecule must have anisotropic polarizability. तो जैसा मैंने H2 molecule के बारे में आपको बताया, as you along the bond axis, so refer to my previous class. I have shown that along the bond axis you have greater polarizability. When we are viewing this, and this is your this is the hydrogen nuclei. This is when you represent the electron cloud like this. So this, when you apply electric field along this direction, electric field, greater distortion is produced. We say it is greater distortion of electron cloud, so greater polarizability along this direction. When you apply electric field along a different direction, say perpendicular to it, if you apply electric field in this way, you will have, along this direction there will be less polarizability. So in this direction there will be less distortion. We say that less distortion of electron cloud, right? Because there are not enough electron in this direction, so less polarizability. And this is what we mean by saying that we have anisotropic polarizability in hydrogen molecule. So that is an essential condition for a molecule to be Raman active. Hello. So ओके, थोड़ा सा लगता है कि बीच बीच में कनेक्शन उड़ गया था, इसीलिए ऐसा हो रहा है. सो अनाइसोट्रोपिक पोलराइजेबिलिटी की बात की थी पिछले क्लास में भी, हमने बताया था. हाइड्रोजन मॉलिक्यूल का एग्जांपल देखिए. अलोंग द बॉन्ड एक्सिस यू हैव इंटरन्यूक्लियर एक्सिस. अगर आप वो करते हैं, इलेक्ट्रिक फील्ड अप्लाई करेंगे तो ज़्यादा डिस्टॉर्शन प्रोड्यूस होगा. वी से दैट तो अनाइसोट्रोपी, सॉरी, पोलराइजेबिलिटी ज़्यादा है. लेकिन अगर परपेंडिकुलर टू द बॉन्ड एक्सिस आप इलेक्ट्रिक फील्ड अप्लाई करेंगे तो distortion will be less, distortion of the electron cloud will be less. And that is what we mean by saying anisotropic a hydrogen molecule has anisotropic polarizability, और वो essential condition होता है Raman activity के लिए. So that was simplest example that we can take and try to understand the Raman activity condition for molecular rotation or vibration to be active. so at least what we expect is that for something to be active, Raman active, there must be change in the polarizability in any of the components. तो थ्री components हमने आपको बताया polarizability का, either shape में change होना चाहिए, जो it is a tensor is represented by, it has magnitude, direction and also three dimensional shape. So either shape change हो या फिर उसका मैग्नीट्यूड चेंज हो, मतलब जो थ्री डायमेंशनल शेप बन रहा है उसका साइज वाइज चेंज होगा, या फिर ओरिएंटेशन चेंज होगा। इन तीनों में से कोई एक चीज चेंज होगा तो रमन एक्टिव होगा। ओके, सो दैट इज व्हाट फर्स्ट थिंग दैट वी लर्न। Then we draw the polarizability ellipsoid as the inverse of 1 by alpha. Alpha is the polarizability. Alpha is the mathematical जो मैथमेटिकल डिस्क्रिप्शन दिया जाता है वो अल्फा से दिया जाता है, इट इज डिनोटेड बाय अल्फा। So 1 by under root alpha is the, and choose a center of gravity and then draw 1 by under root alpha in, so different directions में जो polarizability होगी उसके अकॉर्डिंग से वो स्केल मेजर एंड माइनर एक्सिस ड्रॉ किया जाता है। ओके, सो what we now understand is scattering is different. It is oscillating dipole phenomena. We learnt about that, and we also, we in the last class we also learned what is the, how the scattering, the intensity of scattered light will depend on what are the factors. So the main factor is this d alpha by dq. So q is the coordinate, vibrational coordinates, and alpha is the polarizability. तो पोलराइजेबिलिटी के तीनों में से किसी एस्पेक्ट में, डायरेक्शन, मैग्नीट्यूड या फिर शेप, किसी एक चीज में चेंज अगर हो रहा है तो रमन एक्टिव होगा, और जितना ज्यादा चेंज होगा, हायर द वैल्यू ऑफ दिस, मोर इंटेंस इज द सिग्नल, हायर इज द वैल्यू, more intense, you will have more intense signal. Okay, so in the same way, if the incident light, incident laser intensity of incident laser, so higher this, higher the intensity, greater will be this intensity. So इंटेंसिटी, तो ये सारी चीजें हमने डिस्कस की थी कि चेंज इन डी अल्फा बाई डी क्यू एट द इक्विलिब्रियम, वेरी क्लोज टू द इक्विलिब्रियम पोजीशन शुड बी, ये जो यहाँ पे जीरो लिखा है ये लिखा है एट क्लोज टू इक्विलिब्रियम, दैट मीन्स इन टर्म्स ऑफ व्हेन इट इज वाइब्रेटिंग, तो मीन पोजीशन से के पास जो डी अल्फा बाई डी क्यू का वैल्यू है, जो वो जितना हाई होगा उसका स्क्वायर फंक्शन है। सो क्लोज टू इक्विलिब्रियम और मीन पोजीशन, ये चेंजेस हम देखते हैं। वी ऑब्जर्व द वैल्यू ऑफ डी अल्फा बाई डी क्यू, द चेंज इन पोलराइजेबिलिटी विथ रिस्पेक्ट टू द चेंज इन कोऑर्डिनेट्स, ओके, वेरी क्लोज टू द मीन पोजीशन। वो वैल्यू अगर आपकी काफ़ी ज़्यादा है तो वो इंटेंसिटी ऑफ द सिग्नल विल बी हाई। इंसिडेंट लेज़र का अगर सिग्नल अगर इंटेंसिटी ज़्यादा है तो वो भी हो सकता है, दैट इज अनदर फैक्टर। सो टू फैक्टर्स कंट्रोल द थिंग, वन इज रिलेटेड टू पोलराइजेबिलिटी चेंज इन पोलराइजेबिलिटी जो यहाँ से आया, और दूसरा इलेक्ट्रिक फील्ड वाला जो इंटेंसिटी इंसिडेंट लेजर से आ रहा है। सो दिस इज हाउ द थिंग्स आर रिलेटेड, एंड वी आर गोइंग टू लर्न हाउ टू ड्रॉ दिस पोलराइजेबिलिटी एलिप्सॉइड, एंड ये हमने शुरू किया था लास्ट क्लास में। Polarizability must change linearly with the vibrational motion. So for this, for if you want for it to be for the Raman scattering to occur. So greater is the change in polarizability, more intense is the Raman scattering. Okay. So if there is no change, very close to the equilibrium position, if the polarizability remains unchanged, d alpha by dq is 0, then no Raman scattering will be observed. So ellipsoid, as I told you, is the geometrical surface, something like this, whose all the, if you cut a cross section, it will be appear like ellipse or circle, as you can see here. So basically this is your ellipsoid. So when you are looking at hydrogen molecule, this is what it looks like. So it is a one, so you have greater polarizability. So when you apply electric field, apply electric field in this direction, and then we are drawing this picture that we have. So along this, you know, the there will be greater distortion of the electron cloud, so there is more polarizability, there is greater polarizability in the direction, in this direction. And so we say that this is your under root 1 by under root alpha. So greater polarizability, तो 1 by under root alpha कम हो जाएगा, तो it will be represented by a smaller axis. This becomes a minor axis for the ellipsoid along, ऐसे जब हम ड्रॉ करते हैं. और दूसरे डायरेक्शन में जो इस ऐसे अगर हम व्यू कर रहे हैं, तो ये वाले में पोलराइजेबिलिटी कम है, तो ये एक्सिस जो है वो लॉन्ग हो जाएगा. अब इसी को आप व्यू कीजिए जब ये एक हाइड्रोजन स्क्रीन के पीछे है, एक स्क्रीन, फ्रंट ऑफ द स्क्रीन, बैक ऑफ द स्क्रीन, स्क्रीन के पीछे, बिहाइंड द स्क्रीन. सो ऐसे में अब आप इलेक्ट्रिक फील्ड अप्लाई कर रहे हैं, तो इस डायरेक्शन में आप कहीं पे भी अप्लाई करेंगे, तो हर डायरेक्शन में एक ही पोलराइजेबिलिटी दिखेगी. ऐसे अक्रॉस अगर हम देख रहे हैं, तो ये एक स्फीयर जैसा अपीयरेंस आता है. या अगर आप ऐसे देखना चाहें, तो सो दिस इज द सेम लुक फ्रॉम अ डिफरेंट एंगल. द एलिप्स looks like a sphere when we are viewing it along a different action from the other side. So this is the view of the at the right angles, polarizability ellipsoid at right angles. So जहाँ पे polarizability ज़्यादा है, axis वहाँ पे short हो जाएगा, it will be smaller, and vice versa. So when we are drawing like this, okay, so in case of any other, uh, so polarizability ellipsoid has a circular cross section in, when viewing, when you are viewing it perpendicular to the bond axis, and that's what we were looking at. ये पूरा एक circular जैसा दिख रहा है, and we see it is like a tangerine जो होता है वो it is थोड़ा सा चपटा होता है. यहाँ पे आप देख रहे हैं, the look is different, is not a total spherical like thing. ये orange में spherical होता है, ये this is not completely spherical. It is so for all diatomic molecules the appearance will be something like that. For all diatomic molecules the polarizability looks like a tangerine. That's what we say. So COHCl, that is the diatomic molecule like that, or any other polyometric CO2 ethylene, have same general shape, and they only differ in the size of major and minor axis. Okay, so this was very important because for diatomic molecules in particular, homonuclear diatomic which has no dipole moment, there was no way you could find the rotational constant, and if you are not able to find the rotational constant you can't find the bond length. So ये सारी दिक्कतें थी जब तक कि रमन स्पेक्ट्रोस्कोपी नहीं आया था. So that is the greatest advantage of Raman spectroscopy, that a large set of molecules which you were not able to understand, you were not able to understand their vibrational rotational motion, And so you could not calculate the bond length and other things by this. Now you are able to do so by performing रमन स्पेक्ट्रोस्कोपी. रमन स्पेक्ट्रम आप रिकॉर्ड करते हैं और रोटेशनल रमन, वाइब्रेशनल रमन करके आप ये सारी चीज़ें इंफॉर्मेशन निकाल लेते हैं. सो दैट इज द ग्रेटेस्ट एडवांटेज. So this is the picture polarizability ellipsoid drawn for water in three different directions. So polarizability ellipsoid seen along three coordinates axis. So x y z तीन तरह से देखा गया है. So in the first case, the three atoms are in the screen of the lying in the screen. Then the polarizability ellipsoid, it is most polarizable along this direction. So higher polarizability, the ellipsoid has, so because it is 1 by alpha thing, 1 by under root alpha, so smaller axis. When you, so we are viewing something like this, we are applying electric field in this direction, and then we are viewing. So जब perpendicular हो गया, hydrogen एक पीछे हो गया, oxygen in the screen and another hydrogen in front. So in that case, the polarizability is very, very less along when you are viewing in the direction of the electric field. So this is the least polarizability in this direction, और इसीलिए बड़ा सा वो एक्सिस ड्रॉ किया गया है. So this is a three-dimensional view that you have. The third extreme case is when it is almost linear position में आ रहा है, three coordinates. तो ऐसा ellipsoid. So there are three views of the same thing. CHCl3, CHCl3, you have chloroform polarizability ellipsoid from across and along the symmetry axis. So this is the principal axis. इसके along, so more electron cloud on this direction. So this is your highest polarizability here, like this. Okay, so let's try to see what so what must change if a vibration is Raman active. Polarizability of the molecule must change. What aspect of polarizability must change? Either direction, magnitude, or the shape. So tensor hai, polarizability is a tensor, so we have any of the three things. So this is del q by, so look at this. This must not be 0. It must have a finite value, non-zero value, very close to the equilibrium. So if this is the q, look at this thing. We are looking at this very close to the equilibrium, close to the mean position or equilibrium situation. So observe the d alpha by dq here, d alpha by dq when q tends to 0, when there is so that's it, what is represented here. This 0 is shown here as the subscript. Okay, so when about very close to the mean position, as the molecule vibrates, what is the change in the polarization? What is the slope? So you try to find the slope very close to the thing, d alpha by dq. If it is changing, so then it is said to be Raman active. So in the first picture, and on the left hand side, this is, so d alpha by dq is positive here, so this must be active, Raman active, very close to this point, Raman active. If something like this happens, then you can see very at the equilibrium position, d alpha by dq is 0. Okay, so ये स्लोप होगा, स्लोप का वैल्यू यहाँ पे ऐसे आएगा. So the polarizability when plotted against q, if you are able to find out, so if it is 0, uh, inactive. So this will be Raman inactive in such case. So we have to look at it in this way. Now look at water. Symmetric stretching. Symmetric stretching mode. So what is happening here? See, the first one, you have most stretched conditions. ये equilibrium or mean, then this is stretched, and this one is contracted. Three situations. As the molecule is undergoing vibration, so you have highest polarizability. अब ये दोनों एक साथ स्ट्रेच आउट होगा हाइड्रोजन एटम, तो जो पोलराइजेबिलिटी एलिप्सॉइड है वो उसमें polarizability will be greatest in this case. In the stressed condition, the electrons are not strongly held, they are loosely held, they are spread out over a greater region, they occupy a greater volume, so more polarizability. So you have a greater polarizability in this case, and the ellipsoid will be having a smaller axis. Smaller axis, high polarizability. So ये रिवर्स चलता है, ये आपको समझ में आना चाहिए. इलेक्ट्रॉन क्लाउड का व्यू अलग है, और पोलराइजेबिलिटी का जब हम एलिप्सॉइड ड्रॉ कर रहे हैं वो इनवर्स ऑफ द 1/अल्फा है. सो जिस डायरेक्शन में ज़्यादा डिस्टॉर्शन प्रोड्यूस होगा पोलराइजेबिलिटी ज़्यादा होगी, और एक्सिस पोलराइजेबिलिटी एलिप्सॉइड में जो एक्सिस ड्रॉ करेंगे वो छोटा होगा. अब बीच वाले कंडीशन में पोलराइजेबिलिटी इंटरमीडिएट होगी, तो थोड़ा सा बड़ा, और कॉन्ट्रैक्टेड कंडीशन में सबसे कम होगा, लीस्ट polarizable in this condition. Under this condition, this is more polarizable on the left hand side, and so larger axis. है ना, तो सो इस डायरेक्शन में जो हम देख रहे हैं, so what is happening when there is symmetric stretching? There is change in the ellipsoid size. Ellipsoid size is changing. So this is Raman active. We say that this is Raman active. Okay. So at least one aspect is changing, that is the size. So size of ellipsoid is changing when water molecule undergoes vibration, this kind of symmetric stretching vibration. In the same way, if you look at the polarizability ellipsoid during uh, bending mode, so bending vibration, consider bending vibration. So polarizability is again, so consider you are flying electric field along this, then during the bending mode, जब वो इस तरह से होगा सबसे ज़्यादा पोलराइजेबिलिटी होगी, इलेक्ट्रॉन्स क्लाउड्स का इंटरेक्शन इलेक्ट्रिक फील्ड के साथ अच्छा होगा, द मॉलिक्यूल्स आर the nuclei is not able to hold on to the electrons here, and you have a greater, so smallest, so this way, then the change in axis, and when, so there are two things. On the one extreme, this, when bending is happening, one extreme it is trying to be almost getting linear in the on the left side by HOH, trying to be just less than the linear situation. And when it is on the right hand side, extreme condition kya hai? You have a condition where the two hydrogen atoms are approaching each other. The two OH bonds are becoming collinear. They are almost superimposed over one of the other in the extreme situation. So, so in that situation, the polarizability along this axis would be, polarizability is less along this direction, but इस direction में polarizability ज़्यादा होगी. So this is why the shape of polarizability has changed over here. So what is here? We observe the shape of is changing. Shape of ellipsoid. So this mode is also Raman active. Now when और जब asymmetric I think there was network problem. मेरा कब उड़ गया मैं तो बोलता रहा. Okay, anyway it is recorded. So मैं दो चीजें बता रहा था. So what was I was talking about is this. So पहले हमने symmetric stretching की बात की, and we found that in this particular case the polarizability ellipsoid, the size is changing. In the second case, when we are talking about bending mode, we find a careful analysis will tell you that there is change in shape of the ellipsoid. So this is also Raman active. In the third one, so now we are at the third one. This is the asymmetric stretching mode, and in this case there is one of the bond is stretched, another one is compressed in one extreme, another extreme is this one is now compressed, this one is stretched. So overall situation is that you have an ellipsoid. When you view it like this, it is tilted along a particular axis, this like this. So in this case, asymmetric stretching mode, the ellipsoid orientation is changing. That is, you are talking about direction. So the direction, the 3D orientation has changed. So this mode is also Raman active. So all the three modes of water is Raman active, and रमन एक्टिव होगा, और इस वजह से आपको रमन स्पेक्ट्रा मिलना चाहिए जब आप when you are recording it, it should be seen. So तीन मोड है और तीनों मोड रमन एक्टिव है, बट रीजन अलग अलग है. एक में सिर्फ so in one case there is only one aspect of the polarizability that is changing, that is size. Symmetric फिर bending mode में there is only the other aspect, that is the shape is changing. In third case it is the orientation, the direction of the ellipsoid, that is changing, or that's why. So we expect all the three modes to be Raman active. And just a moment. So this is your spectrum of water. So we have situations that these 32 around 3400 350. So there's peak and bending mode observed over here. Okay, so this kind of situation so we have already discussed these points what are there. So this is also written. So if you are following Banwell, these points are very well given. So we have so bond is stretched, the electrons forming the it are less firmly held by nuclei and more polarized. So that's what how we are drawing the shape of ellipsoid. We are considering each of these things. Okay, so how this when it is compressed. So I have already discussed this point. Bending point motion, the shape of ellipsoid changes. We have seen that, and in the third case, last case, asymmetric stretching, it is the size and shape remain constant, but the direction of the major axis is changing. So this, so all these three vibrations show at least one aspect that is changing, and all are Raman active. Okay, and that's what the Raman spectrum is. In a similar case, in a similar way, we can analyze the CO2 vibration. CO2 vibrations, symmetric stretching mode. Again, so this is how it is a linear molecule. It has greater polarization in this direction, so the axis will be shorter drawn. So this is your symmetric stretching, stretched. This is contracted or compressed, and this is the normal situation, mean position. So in this case, the extent of polarizability changes equally in all the two axes, and so shape is unchanged. So there is no change in shape, but there is a change in, so there is change in size. So size, ellipsoid का size change हो रहा है. So this is Raman active. और इसका जब हम डी अल्फा अल्फा वर्सेस क्यू अगर हम देखें तो डी अल्फा बाई डी क्यू दिस इज पॉजिटिव. So this is very close to the equilibrium. This is positive. So it is a non-zero value and it is Raman active. In other case, bending mode, the polarizability ellipsoid, you can see the shapes are changing like this, and if you calculate d alpha by dq, it is 0. In this case, d alpha by dq is 0, inactive. So very close. So you draw this slope. So here the overall changes, जब कम इधर बेंडिंग हो रहा है, दोनों एक्सट्रीम पोजीशन में changes are equal as compared to the equilibrium position. So both cancel out and you have a situation like this. Very so left side, right side, from the equilibrium position you have same change, and overall d alpha by dq turns out to be 0. So it is inactive. And the third case, asymmetric stretching, again you will find that compression, elongation, compression, elongation, like that. So if this is equilibrium situation, overall thing is that it will be, again, very close analysis tells us that when we see the ellipsoid, there is no change. The slope is remains unchanged. D alpha by dq is 0, very close to the nucleus, and so it is inactive. So it is also inactive. So this is what our thing is. We find that symmetric stretching mode is Raman active, and other two are inactive. In the infrared, you find the other way around. These two are active in infrared, and the symmetric stretching mode is inactive. So this is, now we are at a point what we know as the mutual selection rule. If a molecule has center of symmetry, then this is empirical observation कि अगर सेंटर ऑफ सिमिट्री है तो ऐसा पाया गया कि जो मॉलिक्यूल रमन एक्टिव होगा वो इंफ्रारेड इनएक्टिव है, और इंफ्रारेड एक्टिव जो मोड से दैट विल बी Raman inactive. So this kind of situation arises in molecules having center of symmetry. It is a very useful conclusion कि बहुत जल्दी आप सेंटर ऑफ सिमेट्री है कि नहीं स्पेक्ट्रम देख के बता सकते हैं, दोनों स्पेक्ट्रम आपके पास हो तो. इस तरह से CO2 का रमन स्पेक्ट्रम usually it is seen over here, okay, and infrared spectrum is here, okay. So infrared usually रमन स्पेक्ट्रम में जो सिमेट्रिक वाइब्रेशन है वही सबसे ज़्यादा इंटेंस आता है. रेस्ट ऑफ इट okay, symmetric vibration is, so this is your symmetric stretching, the Raman active. This is your asymmetric stretching. So you see the scale, this is 4000, this is 0. So wave number is in the reverse order, and this is percent T. Negative peak means absorption of light. So this is your asymmetric stretching. So both Raman and spectrum, and this is bending, lower energy transitions. So this is how the spectrum will look like when you compare the IR and Raman spectrum for CO2. So you get two peaks in case of infrared spectrum. So that is one corresponding to bending and asymmetrics, both are infrared active, and only one mode is active in case of, that is the symmetric stretching mode. Okay, so we are now at the very important conclusion regarding this mutual exclusion principle. For molecules with center of symmetry, no IR active transitions are Raman active and vice versa, or IR active molecule not Raman active. So you can state it in either way. किसी भी तरह से आप उसको लिख सकते हैं, Raman active vibration और not IR active, अगर center of symmetry है तो. और एक चीज इंपॉर्टेंट है, all symmetric vibrations very very intense, बहुत ही हाई इंटेंसिटी वाली रमन सिग्नल आएगी. नॉन सिमेट्रिक ones are usually weak and unobservable sometimes, बिकॉज इतना स्मॉल चेंज होगा कि कई बार डिटेक्टर नहीं पकड़ पाता है. सो विल डिस्कस द नेक्स्ट पार्ट द. अच्छा, एक और हाँ जो ऑब्जर्वेशन है कि कुछ रमन सिग्नल जो आता है, जो फोटॉन्स आ रहे हैं वो पोलराइज होते हैं, पोलराइजेशन. तो उस एस्पेक्ट को भी हम लोग कवर करेंगे नेक्स्ट क्लास में. ओके, सो विल टॉक अबाउट द polarization of Raman lines. Polarized, some of the light, scattered light in the Raman, when we perform Raman spectroscopy, appears to be polarized. और वो किस कंडीशन में होगा नेक्स्ट क्लास में डिस्कस करेंगे. ओके, सो